and we'll go from current slide. All right, just a couple of announcements first. They're not really urgent, but they are there. It's been a long time coming. I'll explain part of the situation here. We are working on trying to get the spring and summer schedule straightened out. And I know people are already able to register for some classes, but there have been so many changes this year, major changes, especially in developmental math and in Math 100. We changed for this fall, and then we changed again for this spring. So, and the summer should be a lot like the spring, only it's different because it's only 10 weeks rather than 16. So things change there too. So we're in the middle of trying to straighten all that out, and it has had me just about every minute I'm in the office that I'm not either advising students or tutoring students. I'm working on the schedule, and I've got all the developmental, I think, pretty much taken care of, and I'm working on the Math 100 now, and it is a mess, and every time I do something, someone else goes in and changes something else. So I'm trying to get that ironed out now. But hopefully one of these days it's going to be through, and I'll get back to grading. But I did get all of your first tests graded, those that have been turned in. There's still 1, 2, 3 that haven't turned in the first test, so I need those. And you already have the second test as well, so please be working on those as well. So there's that. And the other thing, and this isn't crucial to this class, it was for my first class, but it isn't for this one, but it's still crucial for you as people. What's next Tuesday? Second? Voting, absolutely. Please vote. Make a plan. Know when you can get there, when you for instance, for me, I teach until 7:45 on Tuesday and Thursday evenings. No way I can get to the polls after work. So I've got to go to the polls on my way into work, and that's what I was telling my first class. If it is really crowded, that would be a great sign. I really love to see big crowds at polls, but I might be a little late getting here. But I'll be here for this class. But I told my first class I might be a little on the late side for the Tuesday. But I think I'll get here in time because classes don't start till 8:30. Surely I can make it by then. All right. So please vote. Please, all of you. All right. Any questions on anything we've done so far? Okay. Well, Chapter 5 is analytic trigonometry, and 5.4 are the sum and difference formulas. Now, some of these you use quite a bit, and some of them only in rare circumstances, so you can always look them up. Everything in here isn't worth memorizing or trying to get, but get the big ones, and we'll talk about what those are. The objective here is to use the sum and difference formulas to evaluate trigonometric functions, verify identities, and solve trigonometric equations. That's why we do all this. That's why we're doing everything we're doing in this chapter, so we can simplify, evaluate, verify, and solve. Okay? That's the whole purpose. So, we're going to start with sum and difference formulas. Okay? And these first ones are pretty important. Well worth your paying attention to these. So you use them frequently enough, you get to know them. Okay? So we'll study the uses of several trigonometric identities. And here are the sum and difference formulas. The sine of u plus v. These are two different angles you're adding together, and you're trying to take the sine of the sum. Okay? Well, here's the formula for it. It's the sine of the first times the cosine of the second plus, same sign here, cosine of the first plus times the sine of the second. That's a fairly easy one to remember. Sine u cosine v plus cosine u sine v. Now, if you get that one down, the second one's a piece of cake. Because all you do is, rather than put a plus here, you do a minus, so that would be sine u cosine of minus v. What's the cosine of minus v? Cosine of what kind of function? Even. So that's the same as cosine v. So that doesn't change, okay? And then it's plus, you would say plus cosine u times the sine of minus v. What's the sine of minus v? Well, sine is an odd function, so that would be minus the sine of v, so that's why the minus sign shows up here. Because that sine of minus v makes this a minus. The cosine of minus v doesn't change anything, because cosine is even. So if you know this one, it's easy to get this one. Now, cosine of u plus v is very different, okay? It's cosine u cosine v minus sine u sine v, okay? Now, one way I remember that it's not plus here, because if that was plus, that would almost look like your Pythagorean identity, and it's not, okay, so it can't be that. But the cosine of u minus v, again, cosine u is the same, cosine minus v is because cosine is even, that's the same as cosine v, but then the sine of u, that stays the same, but sine of minus v changes the sign, so that does look a lot like a Pythagorean identity. If u was equal to v, okay? But if u is equal to v, this would be 0, wouldn't it? And cosine of 0 is 1, and that would be cosine squared cosine squared. So sure enough, you could get your Pythagorean identity out of there. Now, the tangent. This is one you don't use a whole lot, so I wouldn't sweat memorizing it, but just know where you can go to look it up if you ever need it. Tangent u plus v is tangent u plus tangent v. All is tangents here, divided by 1 minus the product of tangent u times tangent v. And then when you put a minus in there, because tangent is odd, this becomes a minus and this becomes a plus, because it changes the sign of both of those. Tangent u minus tangent v, over 1 plus tangent u tangent v. Now, we'll do example 1 that shows how the sum and difference formulas enable you to find the exact value of trigonometric functions involving sum and differences of special angles. Okay, it certainly does that, and there's Jake. Again, all Y chromosomes. Okay. We're only missing Josh among the guys. Okay. I think he's falling apart. Okay. Okay. So here's example 1. Now, is this all that necessary? No, not really. You can always just look it up, plug it in a computer or a calculator or anything else. But you can do it without a calculator. Pi 12ths is not one of our favorite angles, is it? But you can get it from some of our angles. What are some of the angles who do have their denominators in 12? Name some of them. What are our favorite angles? Let's go on and name them. Let me get my pen. What are they? Pi fourths, pi thirds, pi halves, and pi sixths. Okay, those are our favorites, aren't they? Let's write those in terms of twelfths, because they're all will go into 12, right? How many twelfths would be pi 6? 2 twelfths pi. Pi fourths would be 3 pi twelfths. Pi thirds is 4 pi twelfths. And pi halves is 6 pi twelfths. Now, I just did that for fun. But how can you get pi twelfths out of those? Let's see the difference between these two, right? Or the difference between those two, either one. Can't use that one, but you can use either one of these pairs. Which one do you want to use? Pi 6 and pi fourths, or pi fourths and pi thirds? I don't care. Pi fourths and pi thirds, these two right here. Okay, so you could say then that sine of pi twelfths is the same as sine of pi thirds, you said, right? Minus pi fourths. So that would be 4 pi twelfths minus 3 pi twelfths would be pi twelfths, right? Now, what did our difference formula tell you sine was? Yeah, that the pi thirds would be the u. That would be sine of pi thirds times cosine of pi fourths, right? And it's a difference, and this happens to be for the sine, that is a difference, minus, help me, cosine pi thirds times sine of pi fourths. Okay? And since these are our favorites, we know what they are, don't we? What is sine of pi thirds? Square root of 3 over 2. Cosine of pi fourths is? Square root of 2 over 2 minus, and what's cosine of pi thirds? 1/2. And what's sine of pi thirds? Pi fourths? Root 2 over 2. Okay, let's multiply those together. This would be root 6 over 4 minus what? Root 2 over 4, which would be the square root of 6 minus square root of 2 all over 4. Okay, now that's an exact answer. Big deal, okay? Not very usable, but that's an exact answer, and you didn't have to evaluate, you didn't have to pull out a calculator. To get what the value is, you have to pull out a calculator, but that is an exact answer, okay? So any trig function, or at least sine, cosine, or tangent, that can be written as a sum or a difference of all the ones we know, then we can get exact answers without even evaluating the trig function, without going to a calculator or something else. But of course, to get the value of it, you would have to go to a calculator, because I don't know what square root of 6 is. I have a good idea what square root of 2 is, but I don't know the square root of 6, so I would have to pull that up. So that's what they get in the text as well. Let's see how they did it. I can't remember which one they used. Yeah, they used pi thirds and pi fourths too. Okay. You could have used pi thirds, pi fourths, and pi sixths, but we both chose this one. And then the sine of u minus v would be sine pi thirds, cosine pi fourths, minus cosine pi thirds times the sine of pi fourths, which, just like we did, is root 3 over 2 times root 2 over 2 minus 1/2 times root 2 over 2, which is root 6 minus root 2 over 4. And if you try that on the calculator, either sine of pi twelfths, you'll get an answer like this, or if you plug those values in, you'll get an answer like that. To probably as many digits as your calculator will show, they will agree. Okay. Not a very useful application of the sum and difference formulas, but still one all the same. We will find some more useful ones later. There is a checkpoint, and it says find the exact value of cosine pi twelfths, so you should be able to do that fairly easily as well. All right. Any questions? They skip 2, 3, and 4. Oops. So let's do example 2 here. Find the exact value of cosine of 75 degrees. And again, that's not one of our favorites, is it? So what are our favorites? 30 degrees, 60 degrees, 45 degrees, 90 degrees, okay? And anyone see a way to get 75 out of any of those? What's that? Add these two together. So that'd be the cosine of 30 degrees plus 45 degrees. That's 75 degrees, sure enough. And what's the cosine sum formula tell you? Cosine of a sum is .30 degrees times the cosine of 45 degrees. What SIGN sign? Minus sine 30 degrees sine 45 degrees. Okay, what's cosine of 30? Say again? Nope, sine of 30 is 1/2. Square root of 3 over 2. Cosine of 45? Square root of 2 over 2. Minus, what's sine of 30? 1/2. And sine of 45? Root 2 over 2. Okay, and this would be over 4. Hey, that's the same thing we just had, isn't it? Anyone tell me what pi 12ths is in degrees? Okay, that takes a little bit of effort. Pi 12ths is to x as pi is to 180, right? That's our ratio, right? So that would be x is equal to 180 over 12, which would be, second, 15 degrees. And the sine of 15 degrees, how is 15 related to 75? Complementary angles, and the cosine of the sine, yeah, those are the same. So not at all surprising they're the same values. Okay? The sine of the complement is the cosine of the angle, or the sine of the angle is the cosine of its complement. Whatever. So yeah, not surprising they come out the same answers. Okay. Now, they skip example 3, 2. Let's do that one. And by the way, every one of these examples has a checkpoint after it, and good idea to do those as soon as you can after class, just while it's fresh on your mind. Now here's one. Find the exact value of sine of u plus v given that sine of u is equal to 4/5, where 0 is less than or equal to, well, actually less than u, less than or equal to no, less than pi halves. Okay, and cosine v is equal to negative 12/13, where pi halves is less than v is less than pi. Now, does that make sense? Any of this? Sine u is positive where? First quadrant, right? Everything's positive in the first quadrant. That's 0 to pi halves. So yeah, that makes sense. Cosine, they say, is negative. Is cosine negative? Where is this? Second quadrant. Is cosine negative in second quadrant? Sure it is. So yeah, this makes sense. Okay? So since we know that, what would be sine of u plus v from our sum angle formula? What would that be? Okay, sine u, cosine v, right? Continue. Plus cosine u sine v. Okay? Now, I'm kind of okay with that because we know what sine u is and we know what cosine v is. That's fantastic. But we know what cosine u is. They don't tell us, do they? But do they give us enough information we can figure it out on our own? Sure. Okay. And what I like to do in a case like that is draw a circle. Okay. I'll draw the circle first and then fill in the things. I want this to be a 5 circle, not a unit circle, a 5 circle, because our denominator is our radius, exactly. So this will be 2, 3, 1, 4, and 5. 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 Okay. And we know we're in the first quadrant with u. Okay. I'm in the first quadrant with u. Wow, isn't that nice? Okay. And my opposite is 4. So the opposite is the y value. So the y value here is 4. And this is 5. Can anyone tell me what the x value is? I'm sorry, I wrote that wrong. I wrote it as if 4 was the x. Okay. Here's the 4. Okay. The y value is 4. The r is 5. What is the x? One of the favorite little triangles of all time. 3. 3, 4, 5 triangle, right? So this is 3. Yep, and sure enough, it almost looks like it would be. So this would be 3. So can you now tell me what cosine u is? 3 over 5. So we got this one is 4 over 5. Cosine v is minus 12/13 plus, and this was, you said, was 3 over 5. Now we got to figure out what sine of v is. So this time, I'm going to what kind of triangle, what kind of circle do I want now? Not a 5 circle, but a 13 circle. Yay, that's like so much fun. I can't get these erased well. So let me try to do a 13 circle. Okay. Again, I'll put my crossbars in there. And let's make this 6 and 7.
half of 6 is 3, so there's 1 and 2, 4 and 5, and halfway between 7 and 13, 3 would be 10, so there's 8 and 9, 11 and 12. Okay, this is a mess, but why am I doing in the first quadrant? I don't need that. I need second quadrant, so let me do that. There's 6 and 7, 3, 1 and 2, 4 and 5, 10, 8, 9, 11 and 12. Over here, do the same thing. That's 6 and 7, 3, 1 and 2, 4 and 5, 10, 8 and 9, whatever. Okay. So I'm in the second quadrant. That's the only ones I care about. So cosine V is minus 12. That's the x value. So there's minus 12 way out there. And 13 is the radius. So there is, and this is 13 is the radius, and this adjacent side is minus 12. What does that make this one? Now, don't go by my drawing, but how can we determine that? Pythagorean theorem. 13 squared is 169. Yay or nay? Yeah. Minus 12 squared is 144. What does that leave us? What does that leave us? 25. And what's that the square of? 5. So this is 5 over here. So now we know what the opposite is 5, and the hypotenuse is 13, so sine of V must be 5 over 13. See how we got that? Good old Pythagorean theorem. Okay? Erase this so we can do our math. All right. That would be minus 48 over, is that 65? Yeah, no, yeah, 65. Right? Plus 15 over 65, and that would be minus 33 over 65. So there's what sine of u plus v is. Does that make sense? Now remember, our first angle was u was somewhere up around in there, maybe not exactly. This was my u. This is my v over there. And when you add those two together, where do you think you wind up? Which quadrant? That was my u, 4/5 was my sine. This is my v. I'm over here in the second quadrant. Minus 12 over 13 is my cosine. If you add u plus v, where do you wind up? Which one? Second. I don't think so, because u's bigger than that. It's going to be down here. So you add this to this one, you're going to be down here somewhere. Third one, right? Yeah. You don't buy it, huh? Okay. Because this is more than half of a quadrant. I mean, more than 45 is. Close to 60. This is almost 180. So 60 and 180 it would be 240. And that's somewhere down here between 180 and 270. So you're somewhere down there, and the sine of that, sure enough, is negative. Sine in the third quadrant is negative. It doesn't tell you got the right answer, but
you're in the right ballpark, right quadrant. Minus 33/65. Let's see what the book got. Yes, they got it also. Okay? Any questions on that? I really commend drawing your circles. Okay, that helps figure out these angles when you're not given all the information you do. Use what you got and you can usually figure out the rest. All right, let's do example 4 if there's no questions on 3. Okay. Now, here's another one. All right. Write the cosine of the arctangent of 1 plus the arctangent of x as an algebraic expression. We want to write that as an algebraic expression. Oh man. What in the world are we going to be doing here? What does arctangent 1 connote to you? What is that? Number and angle. Say again? Reciprocal of what? Yeah, I think you're right on this.
Negative 1.
Okay.
1 was a negative 1 to the negative 1 power or something like that.
Okay. I think you're getting close to it. Okay. What do we take the cosine of? Angles, right? And that gives us a number, right? What do the inverse trig function of? Number, and that gives us an angle. So what arctangent 1 is some angle. And let's write that as a equivalent expression, but not using arcs. You want to name this? If that's an angle, you want to give it some name? A, okay. So let arctangent 1 equal A. Keeping in mind A is an angle. Okay, can you write that sentence, that description, as a equivalent expression? But don't use an arc. 1 equal, what'd you say? Tangent of A. Perfect. Okay, now, what angle A, when you take the tangent of it, do you get 1? Pi fourths, exactly, because pi fourths is the bisecting angle, and whatever you do on x is the same as on y, so that ratio is 1. So this we know is pi fourths. Okay. So now we got cosine of pi fourths plus. Okay. Now we kind of need to do the same thing for this one, but let's not use A because we don't want to confuse it. Give me a name for this one. Understanding it is an angle. Say again? B. Okay, very creative. Okay. So can we say B is equal to arctangent x, understanding that B is an angle, x is just some number. Okay? Can we write an equivalent statement? X equal tangent B, right? Okay. Now, with that in mind, we're looking okay.
that is some angle B, and the tangent of B is x. Let's make that x over 1. Is that okay? So let's draw, this time I will do a unit circle because of my denominator. Well, no, that's not a unit circle, sorry.
The second value, the V is a arc cosine x.
What's that?
It's arc cosine x, the V.
Oh, that's arc. Oh, that makes it much better, doesn't it? I was going to say, this is really, this thing. Thank you for. Okay. That's arc cosine. Sorry about that. Arc tangent plus arc cosine. Whoops. That makes it much better. All right.
Would it be, because now aren't you finding the cosine of the arc cosine?
Right. That's exactly what we're going to do. So what is our, I think let's just leave this as arc cosine x. Okay. Now, what's your cosine sum formula?
Cosine U times cosine V.
Okay, cosine pi fourths times cosine of the arc cosine of x minus, right? What? Okay. Yeah. Okay. Now, most of this is pretty easy. What is cosine pi fourths? Root 2 over 2. And the cosine of arc cosine x is merely x. Got it. Minus sine of pi fourths is root 2 over 2. Okay. Now, here's where the circle comes into play. Okay. We'll make this, going back up here to what we did, x over 1. So 1 is our unit circle. Okay. And it doesn't really matter where you choose this. I'll choose it this way. Okay. And x, sort of the nice thing is x is your x value, your adjacent side. So this is x, this is 1. What would this, and this is that angle B, right? That's what you chose to call it. Cosine of B would be x over 1, right? X, okay? So what is this side here? This side right here. Anybody? Is what? It's the square root of 1 minus x squared, right? Because you have a right triangle here, right? This length is x, that length is 1. This would be this squared minus that squared would be this squared. So the square root of this would be this squared minus that squared, 1 minus square root of x. So that's what your, and then the sign is that over 1. So that would be times the square root of 1 minus x squared. Okay. Now what you can do is factor out the square root of 2 over 2. And what you have left is x minus the square root of 1 minus x squared. So that's, this thing here can be written as that algebraic function of x. Okay. Now, they write it slightly differently by putting everything over 2, so that would be the square root of 2 times x. I usually like to put the x in front so you don't get it confused. Minus, minus square root of 1 minus x squared over 2. I think that's how they write it. No, it isn't. Oh, I forgot my square root of 2 here. Yeah, okay. So that's x on the root 2, I forgot the square root, distributes across there, minus the square root of 2 minus 2x squared. Yeah. Over 2. And that's what they got. They write the square root of 2 in front of the x. I'll tell you why I don't like to do that. Yeah, I mean, it's perfectly fine to do it. But if you write the x after that, it's so easy to think that x is in the square root sign. You have to be very specific. And my writing is not very specific. So if I put the x out here, I know it's not under the square root sign. I know the book doesn't like that, but it gives you the same answer. Okay. And they have a checkpoint, which is very similar, but not quite the same. Okay, any questions? These are fun identities, aren't they? Yes. Okay. So let's move on to example 5. It says use a difference formula to prove or to verify a cofunction identity. We know this is true, don't we? That the cosine of the complement of x is the cofunction of x, and the cofunction of cosine is sine. Okay? At least we hope that's true. Let's see if we can do that using our difference formula. What is cosine of a difference? We'll start by asking if that's really true. Cosine of a difference is what? Pretty exciting stuff, isn't it? Okay. What's this cosine of a difference? Pi halves times the cosine of x plus sine of pi halves times sine of x. Okay? The question is that sine x? Okay, well, what's cosine of pi halves? 0. So this term is 0. And what sine of pi halves? 1. So sure enough, you get sine x equals sine x. Yeah, it was right. We were right all along. The cosine of a complement is the sine. Cosine of a complement of x is the same as the sine of x. Perfect. Okay? Let's see if they did it any differently. Okay? using the formula, cosine u minus v would be cosine pi halves minus x, would be cosine pi halves cosine x, plus sine pi halves sine x, and cosine pi halves is 0 times cosine of x will be 0, plus 1, sine of pi halves is 1 times sine x, and sure enough, that's sine x. So yep, sine x equals sine x. Good deal. Now, that was example 5. And by the way, you can go to larsonprecalculus.com for an interactive version of that kind of example. Now, there's a little blurb here. Why they chose now to do it, I don't know, but they did. Hipparchus, considered the most important of the Greek astronomers, was born about 190 BC in Nicaea. He was credited with the invention of trigonometry, and his work contributed to the derivation of sum and difference formula. That's why they did it. Sine of a plus or minus b, cosine a plus or minus b. So way back, oh boy, what did he call them? I don't think he called them trig functions. He called them chords, I think it was, and that was the way he expressed them. And he developed tables of chords, which are basically identical to our table of sines and cosines. Oh, y'all don't remember tables, do you? Because you've had calculators your whole lives. Back in the old days, before calculators, you had to look up sines, cosines, tangents, and tables, and use the tables because there weren't any easy calculators to do. Okay. So, moving on to the top middle part of page 376. Sum and difference formulas can be used to rewrite such expressions as sine of theta plus n pi over 2. Okay, cosine of theta plus n pi over 2. Remember when we had multiple, because sines and cosines are periodic functions, and you could have multiple values that gave you those answers. So it says where n is an integer, and to rewrite these expressions as only involving sine or cosine. Okay? And they call these reduction formulas, for what it's worth. Okay? And I think the next example is going to have us do one. Okay? Except they don't do the next example. So let's us do example 6. I think we can. All right. Write each expression as a function of trigonometric, as a trigonometric function of only theta. So here's what we have: cosine of theta minus 3/2 pi. So write that as a trigonometric function of only theta. So how would you proceed? Use the cosine difference function, and what would that be? A formula. Cosine theta times cosine of 3/2 pi, right? Plus sine of theta, sine of 3/2 pi. Okay? What is the cosine of 3/2 pi? Cosine starts at 1, and pi halves it's fallen to 0. At pi it's negative 1. 3/2 pi is 0 again. So that one is 0. Okay? And this would then be sine of theta. And what is sine of 3/2 pi? Sine starts at 0, and at pi halves it's 1. At pi it's
0, and at 3½ pi, it's -1.
So this will be minus sine theta.
Okay? That's what they're looking for, and that's what they got. All right, that wasn't too bad. Let's do the next one. The tangent of theta plus 3 pi. And do you even remember what the sum of the tangent was? Anybody? Tangent theta plus tangent of 3 pi over anybody? 1 minus tangent theta times the tangent of 3 pi. All right. Anyone know what tangent of 3 pi is? Anybody? Zero, because tangent is periodic with pi, and tangent of 0 is 0, and pi is 0, and 2 pi is 0, and 3 pi is 0. Every pi, plus or minus, is 0. So this is 0, and this is 0. So what are you left with? Tangent theta. Okay? Now, of course, that makes perfect sense, doesn't it? Because it's periodic with pi. So whatever tangent theta was, when you go 1 pi over, it's still tangent theta. 2 pi is tangent theta. 3 pi is tangent theta. Yeah, you're exactly that value. Okay, good deal. And there's a checkpoint there that you can certainly do as well. Now I think we're ready for example 7. Okay, here we go. Find all solutions of sine of x plus pi fourths plus sine of x minus pi fourths is equal to -1. Okay, in the interval from 0 to 2 pi. Find all the solutions in that interval, 0 to 2 pi. All right. In the book, on the slide, they left something off. A bracket. In fact, they left it off in both places. Whoever this graphics guy wasn't doing too good of a job here. Okay. Because you have to have y'all done any computer programming? You have, okay. You know if you open a parenthesis, you better close it. Open a grouping symbol, you better. They left that one off and left that one off. So they're going wacko here because syntax error, syntax error, syntax error, okay. Couldn't do it, okay. So now with those in place, I think we can do it. And what would that be? Sine of x, cosine of pi fourths, isn't it? Okay. Plus cosine x, sine of pi fourths, plus sine x, okay, cosine pi fourths minus cosine x sine of pi fourths, and that's equal to -1. Goodness gracious. Didn't plan too well, did I? Okay. Now, what is cosine pi fourths?
and sine pi fourths. Okay, so you can factor that out, a root 2 over 2, and what you have left is a sine x plus cosine x plus sine x minus cosine x is equal to -1. Agree or not? Okay. Now, what do you notice about that? Yeah. Yeah. So, literally like signs. Okay. Okay. Like terms, there happen to be signs. The cosines add to 0, so you have root 2 over 2 times 2 sine x, so that would just be times sine x, right? Because the 2 wipes out the denominator, is equal to -1. Now what? Anybody? What would you do?
So we're trying to set it equal to, or we're just trying to find the x?
Yeah, you're trying to find x. But let's first find out what sine x is. So what would you do?
Divide the root 2.
Yeah, divide everything by root 2. Okay? That wipes them out over here, and that gives you sine x. And if you don't like having root 2's in the denominator, you could write that as minus second, minus root 2 over 2. Good. If you don't like having -1 over root 2. Both of those are equivalent. Okay? Now what angle x between 0 and 2 pi, or angles x between 0, would give you the sine of that angle would be minus root 2 over 2.
7 pi over 4.
Is what?
7 pi over
7 pi over 4, because first quadrant is positive, second quadrant is positive, third quadrant, that would be, you're in fourth quadrant with 7, so that certainly works.
3 pi over 4.
And what?
3 pi over 4.
Not 3 pi over 4, that's second quadrant. 5 pi over 4. So x is either equal to 5/4 pi or 7/4 pi. Okay, why? Because sine is negative in the third and fourth quadrants. Okay, and so it has to be negative, and it has to be that angle. So that's pi-4 plus pi, which would be 5/4 pi, and 2 pi minus pi-4 reference angle, that would be 7/4 pi. 8/4 minus 1/4 is 7/4. So those are our two angles. Yep, 5/4 pies and 7/4 pi. Okay, so let's us clear this out of the way and see how they did it. And just like you did, do the sum and difference formulas. And when you do all that, you get, because these two add to 0, so you get 2 sine x cosine pi-4 equal -1. But cosine pi-4 is root 2 over 2. So then the 2's divide out. You have root 2 over 2 times sine x is equal to -1. If you divide both sides by root 2, you have sine x is equal to -1 over root 2. And you can rewrite that as root 2 over 2. And what values of x will, between 0 and 2 pi, will give you a negative root 2 over 2. The only solutions in that interval are x equal pi fourths, 5 pi fourths, and 7 pi fourths. All right, good deal. Whoa, that ends the section, but we still have example 8 to go. So let's do example 8. Their title here is an application from calculus. Okay? Here's a verification for us. Sine of x plus h minus sine of x over h. Okay? Let's see. Why don't we just go from there? Okay? I think we can. They do a lot more, show more, but I think we can go from there. What would that be? Sine of x plus h from our sum formula. Cosine h okay, minus sine x, okay, all over h, right? Now, what the key is now is to get your sines together and your cosines together, okay, of x's. Not, the h is just a number, so those are going to be constants. So in the first case, you have a sine x times cosine h minus 1, if you combine these two together, over h, plus cosine x times sine h over h. Okay. Now, the only difference is they reverse these and write it as cosine x sine h over h minus, they put a minus in front, and then do sine x times 1 minus cosine h over h. They flip these and put a minus in front. Okay. Now, I think that's all they wanted you to do. Okay? Now, and you might say, so, okay, what does this matter? Now, if you take, some of you had calculus, some calculus. Okay. If you have, I don't know if you recall this, as h is approaching 0, okay, of course sine h is going to 0 and so is h. So that's what we call an indeterminate form. But the limit of that as h approaches 0, sine h, if you think about it, sine of anything, it cuts through just like this and goes up here and does like this and here like that. And h also is here. Those two almost are on top of each other as this straight line, and the ratio of those is 1, because those are basically the same in a very small range here. As h gets close to 0, they're almost on top of each other, and that limit is equal to 1. Okay? Now, do y'all recognize what this is? It's what they call a difference quotient. Yeah, that is the definition of a derivative.
of sine x. Well, if this is going to 1, the derivative of sine is cosine. And if you got that far in calculus, you know that's absolutely true. Okay? Now, but how about this over here? The limit of this is going to 0, because 1 minus, as h goes to 0, this would be 1. This is 1 minus 1 is 0 over 0. But here, the cosine is up here, and 1 minus that, you're up here on top. Those are almost identical to each other, but their slopes are close to 0. These slopes are 1, those slopes are 0. So sure enough, that goes to 0, this goes to cosine. So the derivative of cosine of sine is cosine. That's where you'll use it. You don't need to know that now, but that's where it'll come into play in calculus. Okay? And there is a checkpoint there which also has you do the cosine, basically almost doing the derivative of cosine. And by the way, that winds up being minus sine, but that's for future reference. Let's see if we can get the vocabulary done quickly. Sine of u plus v, or u minus v would be?
Sine of u times cosine of v minus cosine of u minus sine of v.
Perfect. Okay, wait, times sine of v at the end, right? Yeah, okay. Number 2, cosine of u plus v.
Cosine u times cosine v minus sine u times sine v.
Perfect. Tangent of u plus v.
Tangent of u plus tangent of v over 1 minus tangent of u times tangent of v.
Perfect. Number 4, sine of u plus v.
Sine of u times cosine of v plus cosine v times sine of u.
Perfect. Cosine u minus v.
Cosine u times cosine of v plus sine u times sine v.
Sine v. Perfect. And tangent u minus v.
Tangent of u minus tangent v over 1 plus tangent u times tangent v.
Perfect. Okay, homework exercises here. Any of the odds, 7, either 7 or 9 or both. They're both a Calc Chat. Any of the odds 11 through 25, they're all a Calc Chat. 21's a Calc View. Any of the odds 27 to 33, they're all a Calc Chat. Any of the odds 35 to 39, they're all a Calc Chat. 35's a Calc View. Any of the odds 41 to 45, they're all a Calc Chat. 43's a Calc View. Any of the odds 47 to 51, they're all a Calc Chat. Either 53 or 55, they're both a Calc Chat. 53's a Calc View. Any of the odds 57 to 63, they're all a Calc Chat. 59's a Calc View. Either 65 or 67, they're both a Calc Chat. 67's a Calc View. Any of the odds 69 to 73, they're all a Calc Chat. 73's a Calc View. Either 75 or 77, they're both a Calc Chat. 79's a Calc Chat. There's 2 true false, 81 and 83, they're both a Calc Chat. There's an error analysis if you want to do that at 85, it should be a Calc Chat. Verifying an identity, either 87 or 89, both a Calc Chat. Rewriting trig expressions, 91 or 93, they should be at Calc Chat. 95 is another one at Calc Chat. 99 is a Calc Chat. 101 is a proof. You can do it if you'd like. We'll pick up with 5.5 next time, and I'll try to have your test ready for chapter 5. Yes?
Did you already grade that 6?
I've graded test 1 if you want to see your score. Yeah. I've got to find it in the stack because all those other...
Did you put it in the blackboard?
Not yet. I'm behind the blackboard because I'm trying to get all the spring schedule done.